Okay, I have an amazing integral for you guys today. You could even say this is a golden integral. You'll see why in just a minute. So this is the integral from 0 to 4 of the cube root of the square root of x plus 1 plus square root of x. So this is kind of a tricky integral, although if you've seen some integration techniques, you might be able to handle it. So what I'm going to do is give you a moment to pause the video, try this one on your own, and then we'll come back and look at this. Now, when you're evaluating this, try to evaluate it to the simplest or the most simplified form that you can as part of the evaluation. Okay, let's get started. So what we're going to do to evaluate this integral is use what's called a rationalizing substitution. So rationalizing substitution is something that's often used to evaluate functions that have square roots or cube roots, and especially mixtures of them. And what we're going to do is something that may look a little bit strange at first. We're going to take the entire integrand, so this entire cube root, and we're going to let that be u. Okay, so u is equal to the cube root of square root x plus 1 plus square root x. Now with these rationalizing substitutions, the idea is that you try to solve for x and then differentiate and then get everything in terms of u. So we can immediately cube both sides and we get u cubed is equal to square root x plus 1 plus square root x. Well, what are we going to do now? This is an equation that has two square root terms in it. And you may have seen these type of equations in high school algebra. When you have two terms that have a square root, something you can do is isolate each term individually and square both sides. If you try and square immediately, you're still going to have a square root. So let's solve for the square root of x plus 1. We'll try and get rid of that square root first. So I'm going to subtract square root of x. A u cubed minus square root x is equal to square root x plus 1. So we're going to square both sides. And as I said, that'll get rid of the square root of the x plus 1. So I'm going to square out this binomial on the left. It'll give me u to the 6th minus 2u cubed square root of x plus square root of x all squared, which is x, is equal to x plus 1. Now, there's an x term on both sides, so that'll go away. And what I really want to do is isolate this 2u cubed square root x term. So I'll subtract u to the 6th. And what that's going to give me is a minus 2 u cubed square root of x is equal to 1 minus u to the 6th. Divide by minus 2u cubed. And we've solved for square root of x. Square root of x is equal to, so instead of 1 minus u to the 6th, I'll switch it to u to the 6 minus 1, because I don't like that minus sign on the bottom, so over 2u cubed. And now what I'm going to do is write this a little differently. So I'm going to write this as 1/2, so I'm taking the 2 out. And I'm going to actually divide through by u cubed. U to the 6th over u cubed is u cubed. And then, of course, 1 over u cubed is u to the negative 3. So minus u to the negative 3. I still need to square the square root x. So squared. So I'm going to square all of this. And now I've solved for x. X is equal to, so I square the 1/2, 1/4. And now I've got this u cubed minus u to the negative 3. So if I multiply that out, that's u to the 6th. And then I'll do first squared and last squared, and then do the middle. So it's u to the 6th plus u to the negative 6. And since u cubed and u to the negative 3 multiply to u to the 0, which is 1, it's just minus 2. So this is x. Now, what we need to do is differentiate this. So we're going to get dx is 1/4 6u to the 5th minus 6u to the negative 7th. And the negative 2, of course, does not contribute anything because derivative of a constant is 0. So we've got dx. Now, if we go back up to the integral up here, we can now write this integral using this substitution. The only thing we need to do, though, is figure out what's going to happen with these limits. So x runs from 0 to 4. When x is equal to 0, how does that translate? So that's going to be u is equal to cube root of square root 1 plus square root 0. Of course, that's 1. And when x is equal to 4, u is the cube root of, let's see, square root of 5 and plus square root of 4. So I'll call it 2 plus square root 5. Okay, so now we can write down our new integral entirely in terms of u. So what we have is the integral from u equals 1 up to u equals cube root 2 plus square root 5 of, so if we go back up here, it's u times dx. So u times dx, but dx was 1/4 times this 6u to the 5th minus 6u to the negative 7. There should be a du up here, of course. Okay, so this is our integral entirely in terms of u. I can clean this up a bit. There's common factor of 6 I can take out, and it's over 4. So let's write that as 3/2. The integral from 1 to cube root 2 plus root 5 of, so I've got u to the 6th as the u distributes, minus, again, the u distributes and makes it u to the negative 6 du. And these are just powers of u now. So I've got 3/2. This integrates to u to the 7th over 7 minus u to the negative 5 over negative 5. Again, all taken from 1 up to this cube root of 2 plus root 5. Now, the problem here is this is a little strange. Think about trying to substitute the cube root of 2 plus square root 5 into here, raising it to the 7th power, the negative 5 power. It seems a little strange. So what we're going to do is stop for a minute and kind of think a little bit more about what this number actually is. So we could guess what this number is. If you think of different number systems, if I multiply two numbers that are of the form a plus b square root 5, where a and b are integers, I actually end up getting a number of that same form. If you FOIL it out, you'll see that you do get that. So why don't we just guess? Maybe the cube root of this looks the same. So I'll try and guess that this is a plus b root 5, where a and b are integers. Again, we're just fiddling around here guessing. Well, let's cube everything out and see what this would imply. We would have to have 2 plus square root 5 equal to a plus b square root 5, all cubed. Okay, if you know the binomial theorem, this is going to multiply out to a cubed plus 3 a squared b root 5 plus 3 a b root 5 squared, and then plus the b root 5 all cubed. So if we take a look at this, we can put some terms together here. So this is going to be this term. This will also be just an integer, because we're going to get 3a times b squared, and then the square root of 5 is going to get squared to make 5. So this is going to be 3 times 5, which will make 15. So this is all really 15ab squared. So we've got a cubed plus 15ab squared plus, now let's see what our square root 5 terms are here. The b square root 5 all cubed is b cubed, and then the square root of 5 cubed. The square root of 5 cubed is 5 square root 5. So we've got 5b cubed times the square root of 5. And then from here, we've got a 3a squared b. So let me write this as 3a squared b plus 5b cubed times the square root of 5. Okay, so let's take a look at what we have here. If these two numbers are going to be the same in our number system with square root 5, it looks like the 2 should equal all this, and the square root 5 should equal all that. So this should all be equal to 1. So let's set up a little system of equations here. We're trying to solve a cubed plus 15ab squared is equal to 2, and then 3a squared b plus 5b cubed is all equal to 1. So we've got a nonlinear system of equations. There's no obvious way to go about solving this. So what I'm going to do is we're going to look at this system. I'm going to graph it on Desmos in X and Y, see what the graphs of these look like, see if we can look at the intersection point, guess what it is, and then just check it. So we still have to verify it after we look at the graph. So let's look at the graph of these two curves on Desmos. So here I've graphed our two curves, x cubed plus 15xy squared equals 2, 3x squared y plus 5y cubed equals 1. And you can see the curves here. If I back up, you can see they're both asymptotically approaching the coordinate axes. But if I zoom in here, it looks like there's an intersection point somewhere in here. Looks like we have an intersection point, and it appears from the graph, Desmos is telling us this is 1/2, 1/2. So why don't we go back, substitute in 1/2, 1/2 for x and y into the system, and check that this really is a solution. And it looks from the graph that it's the only solution. Okay, so we're going to substitute a equals b equals 1/2. So actually, since a and b are both the same, we can just say here that this is a cubed plus 15a cubed on the left-hand side. Of course, that's 16a cubed. And if a is 1/2, a cubed is 1/8. So 1/8, which is 2. So that checks out. The second equation, again, since a and b are equal, I really get 3a cubed plus 5 a cubed, or 3b cubed plus 5b cubed, which is 8. A cubed, which is 8. Again, a cubed is 1/8. And 8 times 1/8 is 1. Okay, so we do have a solution, which means, okay, what was the point of all this? We can re-express this cube root of 2 plus square root 5 as 1/2 plus 1/2 square root 5, or 1 plus root 5 over 2. Now, this is a famous number. If you're not familiar with it, this is the golden ratio, 1 plus square root 5 over 2. And it's denoted by the Greek letter phi. So what we can do is go up here, and let's just rewrite this. This is 1 plus square root 5 all over 2. Now, this still is kind of a little bit tricky because do I really want to raise 1 plus square root 5 to the 7th power and to the negative 5 power? So maybe there's some pattern to do with these powers here. So what we're going to do next is actually take this golden ratio and see if we can rewrite the powers in a nicer form so that we can evaluate this integral. Okay, so let's take a look at this golden ratio. Phi is equal to 1 plus square root 5 over 2. So we know that phi is going to be the root of a quadratic. Let's see if we can figure out which one. Phi squared is equal to 1 plus square root 5 over 2 all squared. This is 1 plus 2 root 5 plus 5 all over 4, which is 6 plus 2 root 5 over 4, and canceling factor of 2 on the top and bottom, this is 3 plus root 5 over 2. But notice that 3 plus root 5 over 2 is exactly 1 more than 1 plus root 5 over 2. So this is actually phi plus 1. So we see that phi satisfies this quadratic equation. Phi squared is equal to phi plus 1. And if we multiply this equation through by phi, we get other relationships. So phi cubed is equal to phi squared plus phi. But now we just saw that phi squared is phi plus 1. So this is phi plus 1 plus phi, which is 2 phi plus 1. Interesting. Well, let's just keep going with this. Phi to the 4th. If I multiply my main equation up here by phi squared on both sides, I see that phi to the 4th is equal to phi cubed plus phi squared. So each positive integer power of phi is the sum of the two previous powers. And again, let me use what I have from above. Phi cubed is really 2 phi plus 1, and phi squared we have is phi plus 1. So 3 phi plus 2. So it seems to be a little bit of a pattern here. Let's do a couple more. Remember, we have to go up to phi to the 7th. So maybe we can see the pattern before there. Phi to the 4th plus phi cubed. This is going to be 3 phi plus 2 plus the 2 phi plus 1. 5 phi plus 3. And now you might start to see a pattern here if you're familiar with some numbers. What is a sequence of numbers that starts off 1, 2, 3, 5? Can you guess what might come next? Let's see. 5 phi plus 3. Phi to the 4th. 3 phi plus 2. 8 phi plus 5. What we have here is the sequence of Fibonacci numbers. And I'll go one more because we do need phi to the 7th. But I'll also write a formula that I'll ask that you prove if you want to take the time to do that. You can prove it using induction. So the 7th power here is 13 phi plus 8. And here's the general formula. So it turns out that phi to the n is equal to the nth Fibonacci number times phi plus the n minus first Fibonacci number. So this is for n bigger than or equal to 1. And the Fibonacci numbers start with 1, 1, and then, of course, fn is equal to fn minus 1 plus fn minus 2, the sum of the previous two. So 1, 1, 2, 3, 5, 8, and so on. Okay, so for our purposes, though, we have phi to the 7th here. What about the negative powers? What about phi inverse? Well, if we go up to our equation up here, what we can do is divide by phi. So instead of multiplying by phi to get higher and higher positive integer powers, we'll divide by phi. Okay, so let's see what that would give us. We'd get phi is equal to, phi divided by phi would be 1 plus, and then phi inverse. So we actually get phi inverse is equal to phi minus 1. What about phi to the negative 2? Well, if we multiplied by phi to keep getting these higher powers of phi, maybe we can divide by phi. So if I divide by phi here, I'm going to get phi to the negative 2 is going to be phi divided by phi, again, is 1, minus, and then phi inverse. But I already know what phi inverse is. Phi inverse is phi minus 1. So what I get here is a minus phi plus 2. Okay, that's interesting. Let's keep going. Phi to the negative 3. Again, I'll just take this previous equation here and divide by phi. So to divide by phi over here, I've got minus 1 plus 2 phi inverse. And that's going to give me negative 1 plus 2 phi minus 1, which is going to be 2 phi minus 3. Okay, so kind of a similar pattern, but let's see. Divide by phi again. 2 minus 3 phi inverse. Minus 3 phi. And then we've got 2 plus 3, which is plus 5. So you see the Fibonacci numbers are showing up here again. But you also notice there's this alternating sign pattern. Sometimes the phis have positive coefficients, sometimes they have negative, and vice versa for the constants. We needed phi to the negative 5, so we'll go one more. This is going to be minus 3 plus 5 phi inverse. So negative 3 plus 5 phi minus 1, which is 5 phi negative 3, subtract 5 minus 8. Okay, so I will leave it to you to figure out a nice little formula for the negative powers, just like we had for our positive powers up here. But we have the powers that we need. So we have, I'll just kind of summarize here at the bottom, we have phi to the 7th, which is 13 phi plus 8. And we have phi to the negative 5, which is 5 phi minus 8. So now we can take these expressions and use these to evaluate our integral. So I'm going to clean this up a bit. We've got subtracting a negative on the bottom there, so I'm going to make that a positive. And then I'm going to get a common denominator of 35. So we got 5 over 35. Here we have 7 over 35. And if I take that 35 out, we've got 3 over 70 times 5u to the 7th plus 7u to the negative 5, all evaluated from 1 up to phi. All right, so this should be fairly straightforward, at least in terms of phi. 3/70. Okay, we said phi to the 7th. That was 13 phi plus 8. So we've got 5, 13 phi plus 8, plus 7, the u to the negative 5. If I plug in phi, that's 5 phi minus 8. But then I also have to subtract when I substitute in 1. Obviously, that's going to be 5 plus 7, which is 12. So I also have a minus 12 here. Okay, so let's see what we got going on here. 65 phi. This is 35 phi. So altogether, how many phis do we have? 65 and 35. That's 100 phi. And we got 40 minus 56, and then minus another 12. So that's going to be 40 minus 68 minus 28. So again, there's a common factor we can take out here. 3 over 35 times 50 phi minus 14. Now, this is still not the form that we'd like it in, because we'd like it not in phi, we'd like it in terms of square root 5. But this is not too difficult to do, because you just have to remember that phi was 1 plus root 5 over 2. And now we're very near the end, because we have 3 over 35, 50 times phi. So since there's a 2 in the denominator of phi, that's really going to be 25 times the 1 plus square root 5. So that's going to be 25 plus 25 root 5, and then minus 14. So our final result, our evaluation of the integral, is 3 over 35 times 25 minus 14 is 11. So times 11 plus 25 square root 5. And that obviously is the best simplified form that we can express this in. So I hope you like this integral. It illustrates rational substitution, the golden ratio, powers of the golden ratio, a lot of interesting stuff going on. So hope you enjoyed it.